Let's start with an idea that might sound a little bit crazy. That vast, solid, unmoving desert you're picturing in your head, it's not really solid. In fact, it's not even a landscape.
When we look at something like this, we see something fixed, permanent. But that's just our human perception talking. What's really happening here is something else entirely, a system in constant, powerful motion.
Believe it or not, it's an ocean. I know, that sounds wild, but this is the mind-bending idea at the very heart of the sci-fi classic Dune, that a desert is just a river with a totally different sense of time. And today, we're going to unpack the brilliant real-world science that actually makes this possible.
So, the big question is, how on Earth can something as solid as a sand dune possibly behave like a liquid? Well, it all starts by looking at the world in a very specific and maybe a little bit strange way.
It turns out the author of Dune, Frank Herbert, was kind of obsessed with this idea of scale-invariant patterns. Now that's a fancy way of saying he noticed how the universe just loves to repeat itself. The same fundamental shapes and behaviors pop up everywhere, from the tiny ripples on a single dune all the way up to the swirling currents of a massive river.
And here's the kicker. This wasn't just some sci-fi daydream. Herbert's entire vision was actually sparked by a real-world project he saw with his own two eyes.
Okay, so picture this. It's the 1950s, and the U.S. Forest Service is out on the Oregon coast working on something called the Florence Project. Their goal was pretty straightforward. Stop these massive, shifting sand dunes from basically swallowing up roads and towns by planting grass. But while everyone else saw a problem that needed fixing, Herbert saw a process to be understood. He had this incredible insight. He realized he wasn't looking at static hills of sand. He was watching fluid mechanics, just playing out over years instead of seconds.
All right, I can already hear you thinking it. Sand and water? Come on, they're total opposites. And you're not wrong, on the surface. So let's actually put them side by side and see what's going on.
I mean, the differences seem pretty stark, right? Sand is made of these individual, clunky grains. It moves so slowly, we're talking centimeters a day, that to us it just looks totally static. Then you have water. It's made of tiny little molecules, it moves super fast, and you can literally see it flowing. It's the definition of dynamic.
So yeah, they seem like they're from completely different worlds. But what if that's just an illusion, a trick of our own human perception? What if, when you dig down into the physics, you find out they're both playing by the exact same rules?
To answer that, we've got to talk about the physics of flow. And this is where it gets really cool, because it turns out that both systems, the sand dunes and the rivers, they belong to the very same category of physical structures.
They're both what scientists call dissipative structures. Now, I know that sounds super technical, but the idea is actually pretty simple. Just imagine a whirlpool in your sink. That spinning vortex shape, it only exists as long as water is flowing through it and draining out. It has to constantly burn through energy just to keep its form. That's a dissipative structure. And guess what? Both sand dunes and rivers work in exactly the same way.
So the key takeaway here is that both of them need a constant supply of energy to maintain their shape. For sand dunes, that energy is the wind, constantly pushing and shaping the grains. For rivers, it's gravity, pulling the water downhill. See? The energy source is different, wind versus gravity, but the fundamental process of dissipating that energy to create a structure, it's identical.
And this really gets to the heart of it all. The math that describes how sand moves, what we call granular flow, and the math that describes how water moves, fluid dynamics, well, they're incredibly similar. The equations that predict their turbulence, their eddies, their overall behavior, they're basically reading from the same physics playbook. Which brings us to the final and most important piece of this whole puzzle. If they follow the same rules, if they're the same type of structure, what in the world makes them look so different to us?
Okay, so let's recap for a second. We've got two systems, both burning through energy, both following the same physical laws. So what is the one single variable that separates them? The one thing that makes one look like a solid landscape and the other like a flowing liquid.
And the answer, believe it or not, is just time. That's it. It all comes down to the speed at which things are happening. Scientists call this the entropy rate. It's basically how fast a system chews through energy to create order. Sand dunes do this incredibly slowly, so to our eyes they look like a static landscape.
But rivers, they burn through that energy super fast, so we see them as dynamic and flowing. Here's the truly wild part. If you could somehow hit fast forward on a sand dune, its flow would look just like a river. And if you slam the brakes on a river, slowing it way, way down, it would look just like a creeping, solid landscape.
This is really the whole idea in a nutshell. A field of dunes is basically a river that's playing out over a geological timescale. And a river, that's just a dune field with its finger on the fast-forward button. They're the same self-organizing thing, just running at completely different speeds.
So in the end, Frank Herbert's intuition was absolutely spot on. The only real difference between a flowing desert and a flowing river is the speed at which their story unfolds.
And that's got to make you wonder, right? If a desert is really just an ocean in slow motion, what other enormous, invisible flows are out there, shaping our world right under our noses, just waiting for us to change our perspective and finally see them?